Snark Chocolate, a show about ZK products where we break them down with rich flavors and sweet insights. My name is Omer, and I'll be co-hosting this episode together with Queenie. Today, we are thrilled to be joined by the legendary Morten Dahl, VP of Blockchain Engineering at Zama. Morten, it's great to have you here. How about a quick introduction both to you and to Zama?
Hey, yeah, thanks for inviting us to join here on your podcast. So I'm Morten. I'm the VP of Blockchain Engineering here at Zama. Zama is a cryptographic company. We're focusing on full homomorphic encryption. We have a core library, TFHE-rs, which is taking our encryption scheme and then implementing this efficiently for CPU, GPUs, looking at custom hardware as well. And then we're building two applications on top of it. One is around blockchain, and another one is around machine learning. And we're selling this as you can buy a license either to use the core library for your own applications, or you can buy a license for the products that we're building on top of it for blockchain and machine learning.
There's quite a lot going on in the land of homomorphic encryption. I think that we'll be able to only scratch the surface. And I want to just, dive in. So Zama is definitely the leader when it comes to full homomorphic encryption, FHE. I think a good starting point would be to have some kind of a quick overview about your products and solutions.
Yeah, sure. So the Zama as a company is really focusing, as I said, on the full homomorphic encryption. We've done this from the beginning, where we're offering the library for anyone that wants to play with this core technology. So we can think of full homomorphic encryption as kind of like similar to zero knowledge proofs, where you have a core technology and you have various implementations of this that you can then use for building your applications. What we see an interest from researchers to use the library, but we also see interest from various groups that wants to somehow build full homomorphic encryption into the applications. What you can do with full homomorphic encryption is that you can encrypt data like you would typically, but with full homomorphic encryption you can compute on the data while it remains encrypted. So this means that it's not a question of encrypting the data from point A to point B and then decrypting it at point B, doing a computation and then re-encrypting the result. Is really you can keep the data encrypted throughout the entire process. And this gives you some benefits where you can, so if you think of it from a service perspective, so let's take the application of machine learning where someone is offering predictions on your data. In the typical sense, you might encrypt the data as it goes from you to their servers, but then it will be decrypted, it will run through the machine learning model, you will get a prediction, the prediction will be encrypted, sent back to the user who can then decrypt it and see the result. With full homomorphic encryption instead, you don't have to do the decryption step on the server, so you can encrypt the data, you can send the encrypted data, it remains encrypted while you do the predictions, while you run it through the model, and you get an encrypted prediction back that you can send back to the user who can decrypt. So full homomorphic encryption is changing this where you can now control exactly where your data is decrypted, who has access to it, and you don't have to decrypt in order to compute on it. We're taking this core technology, we develop it, we made it efficient, we made it practical in the sense that we're not limited to what kind of functions you can do on the encrypted data. And then we're also building or providing this core technology in a few products. One is around machine learning, as I just mentioned, where we have a compiler, Concrete, where you can express the program in Python and then have this program compiled down to an encrypted version of it. So you write normal Python code, but then you get a binary out of it that will now take encrypted inputs instead of plain text inputs and then do the homomorphic computation according to the Python script. We then have Concrete ML, where we have a few machine learning models that have already been optimized for this encrypted space. And then finally, on the blockchain side of things, we have an integration of the core library, TFHE-rs, into various blockchain frameworks. We're focusing in particular on EVM-based frameworks, where we are then, from From a user's perspective, from a developer perspective, we're essentially adding encrypted data types to your smart contracts that you can then use. We're not changing anything on the software, so you can run this stuff on Ethereum. I think we'll get back into that later. But from a developer perspective, you're now getting encrypted data types, encrypted integers, encrypted booleans that you can compute on the blockchain as if it was ordinary data types, except they remain encrypted. So that's kind of an overview of the products and what we're focusing on. But again, you can use TFHE-rs directly as it is to build your own applications beyond these two.
I think it's quite interesting. So it's one product actually fits different use cases.
Yeah. So the TFHE-rs is really the core technology that we're also offering as a library. It's open source, so you can buy a license for it if you want to use it in commercial settings. And then you could do and do the work on your own, right? You could go and integrate this library into a blockchain, for instance, but that turns out to be non-trivial. So we kind of done that for you and then offering that as a product to make it simply easier to do.
Got it.
So how does it look working on the different parts of these products, blockchains and AI? Like internally, how you divide the work, how you come up with the roadmap? Are these like separate teams? How does it look like?
So we do have two different divisions working for this. You can think of it roughly as being a foundational layer, which is TFHE-rs, which means or includes researchers that are working even at the academic level for optimizing the fully homomorphic encryption scheme, engineers working on CPU implementation and making it efficient, people working on GPU implementation, and then also some interest in custom hardware for speeding it up. So you have like a foundational layer that we can think of as TFHE-rs, which goes from research to efficient implementation on various hardware platforms. And then on top of this, we're building the two pillars. We have a division focusing on concrete and concrete ML, and a division focusing on blockchain.
What can you tell us about the customers of these products? I guess there are like very different types of customers, but is there anything that you can share about like who is using it?
So I'm focusing mostly on the blockchain part of it. So that's where I know the most. We do have customers that are interested in building this into their own blockchain. So they're launching a layer 1 or even a layer 2, and they want to offer this as part of their blockchain. So we do have a few customers that are doing this already. And then we have another solution where you don't have to build your own blockchain for this. So we can offer this available on an existing platform. So think of it as Ethereum. And here we're targeting more app developers that are interested in launching a dApp on let's say Ethereum, as opposed to building their own blockchain. So those are the two kind of segments we're looking at. Both have advantages and disadvantages. Historically, we focused more on what we call the FHEVM native, which is for people that want to build their own layer 1 blockchain. And you're building the homomorphic capabilities directly into the full node software. And then the other vertical, which came later, we announced it this summer, is where if you don't want to change the full node software, if you somehow want to add on to an existing platform, then you can do this as well. We call this the FHEVM co-processor. And the audience there, or the target, is a bit different, as I said. So either the entrepreneur that wants to build their own blockchain and have the advantages that you get from the FHEVM native, or someone that is just interested in building a dApp using encrypted data.
Right. So you mentioned the FHEVM coprocessor, which is new, but also it's something you've been working on for quite some time. Right? There have been some iterations of it in the past. Can you sketch the vision here? Where is it going? And also, I'm curious because we do have this performance bottleneck, right? You also mentioned that you are working on CPU, GPU, and all of that. So now when it becomes like very real, like you have L1s or different like blockchain teams using this technology, is there any is the performance bottleneck still exist? Like how do you even measure performance? How do you see improvement over time? Is there some kind of like a Moore's law here in homomorphic encryption for that?
Yes, a lot to unpack there. So I think starting with the coprocessor, the initial thinking around this was there's two motivations for it. One was we had what we call the FHEVM native, right, where all the full nodes on the network needs to do the homomorphic computations, which to your point are expensive. Those are expensive computations. There's a significant overhead compared to plain text computations. And the FHEVM native was kind of the first iteration of this. What we then saw was there are certain platforms, think of Ethereum for instance, where it's very unlikely that we would go in and build our homomorphic library directly into the full node software. That would simply be too much of a change. So we started thinking, saying, how can we add this to an existing framework without changing the full node software? That was the first motivation for doing this, and that's what we achieved with the coprocessor. And then the second benefit that we get from the coprocessor is that we, instead of doing the computation directly on the layer 1 chain on the full node software, what we do instead is we do what we call symbolic computation on the layer 1. So you can think of this as running the transactions or the computations as normally, but where we are operating on symbolic data types instead. So we're kind of, when you run a transaction on this, you're kind of recording the relationship between data types or values without doing the actual computation. But that means that on Ethereum, for instance, you would then build essentially a computational graph of what needs to be computed. And you get consensus among Ethereum validators that this is really the computation that needs to happen. And then afterwards, on the side, we can use the coprocessor to then do the actual computation, the expensive computation on the ciphertext. But we still get consensus on what needs to happen. We still have a consensus saying a computation took place where A transferred this amount of tokens to B, and this gets settled. But then to do the actual computation of doing the transfer and updating the ciphertext, this then happens on the side on the coprocessor. So the second benefit there is we can scale the coprocessor much better. The computations on chain, they still happen sequentially, but now the symbolic evaluation of this is efficient, but they still happen sequentially. But once we have to do the actual homomorphic computations on the side in the coprocessor, we can scale this out horizontally. And this is working on public data, so it can be publicly verified. Everything is, you just get ciphertext that needs to be computed. So those are the two main benefits. One is with the coprocessor design, we can do this on-chain in the sense that the symbolic computation happens on-chain without changing any of the node software. And then the heavy computation happens off-site on the coprocessor. And since it happens off-site on the coprocessor, it's much easier to scale. What we're then doing to optimize the computation is, of course, we're developing new technique, new algorithms at the core research level for our given encryption scheme. We're improving the implementation at the CPU level, but we're also looking into hardware, as I said. So GPUs are giving a significant boost for some operations. And as a company, we're also making a bet that custom hardware will come in and give us significant speed efficiency improvements over the coming years. But it's true, it's not a silver bullet. We do think that custom hardware could make it bring the performance up to where plain text is today in the future. But in the meantime, it's true, it's not a silver bullet where you need to be a bit careful about what kind of computations you do, in the sense that you don't want to change, just take your latest LLM and start running this on encrypted data. That will be prohibitively slow. But in the sense of, on the use case of blockchain, for instance, we think this is a good middle ground because you're doing relatively simple computations. You're not running through a large model, and these simple computations can also be can already be efficient today. We're seeing transactions around where we can do around maybe 10 ERC20 transfers per second using a normal CPU.
And just a quick follow-up. So the FHEVM coprocessor is different from the ZK rollup setup, since ZK rollups, they only send and store data on layer 1 platforms.
So that's a good question, around what is the difference between the CK technologies for this, or solutions for this, and the full homomorphic encryption. One difference is that with CK, you're essentially keeping the plain text data off-chain, and then you're storing commitments and so on chain, and you're proving that you did the computations correctly on the plaintext data, so that those commitments that you have on chain have the proper relationship between them, that the computations were done correctly. This means, however, that you need someone to keep the plaintext computations off chain. So there's two disadvantages to this. One is someone needs to keep the plaintext data, and it needs to be kept in sync. And the second one is, if you want to mix data coming from different users, then you need this entity that can get to see all the plaintext data. So in the simple use case of an auction, for instance, you would need, maybe if you look purely on-chain, you never see anything except the winner of the auction. But someone needs to collect all the bits in plaintext and do the computation and then push this on-chain. And one question there is then, who is this entity that can do the plaintext computations? Who is this that's trusted to actually see all the bits and then do the honest computation and so on? And the CK solutions, they don't really have a solution to this. This is how they work. Homomorphic encryption, on the other hand, if we stick with the auction, everyone would encrypt their bits. So you get a ciphertext for each bidder. And now you can do the computation directly on the ciphertext. So you don't need to do this off-chain computation in plaintext and then prove that you did it correctly. You can simply just give ciphertext that represents the bits and then run the auction decision algorithm directly on the ciphertext and then choose to reveal only who won the auction. So you kind of get this nice benefit where it's easy to mix data between users, but also between different smart contracts. So again, if your auction is using an ERC20 token, for instance, you can have an encrypted ERC20 token that can then be used by your blind auction, and this would work nicely together, directly on chain.
Great, thanks for the explanation. Sounds really like black magic.
So we do like to, so the technologies, they also, we don't want to pin them against each other too much, because we're also using CK proofs in our system. One is for when you're providing an input, when you're providing a ciphertext, and now it gets a bit technical, so I'll go quick on it, but when you're providing an input, you need to provide a CK proof that this is actually what we call a well-formed or honestly generated ciphertext. And in order to do that, we do have a small CK proof that is proving that this ciphertext is actually a real ciphertext. So that's one place where we're using CK technology. The other one is, at the research level, we're also working on what's called verifiable computation. So think of it in the scenario where someone is running a machine learning model, and now they send an input, and then encrypted input, they have to run this through their model. This would be an expensive computation for them. So they would be incentivized from a financial perspective to run a much simpler model, and then just give you back a ciphertext saying, okay, this was your prediction, because then they saved a lot on compute. So what you want in that scenario, even if they're not learning anything of your data, you would also want them to prove that they actually did the right computation, that they actually ran your input through the big model that you're paying for. And we have this, we can use the same in the blockchain sense, where even if the computation, for instance, is happening on the coprocessor and the coprocessor cannot learn anything, we still need a mechanism to verify that the coprocessor did the right computation. In our case, there's different things we can do, right? We can, as I said, it's publicly verifiable. It's just computations on public ciphertext. So anyone can redo the computation to see if it was lying. So we can do something around fraud proofs. We can replicate it and get consensus and bake it into some or tie it up with some staking. Or we can use verifiable computation where the coprocessor is doing the homomorphic evaluations, but also providing a proof that it did this correctly. And then you can trust the ciphertext. So the two technologies, they definitely have merits, and you kind of need all of it to get the proper solution. I don't know if you want to go into it now, but another technology that also comes into play here is MPC, so multi-party computation, that we're also looking at or also using, and also trusted enclaves, or Ts, which is also something that we're interested in.
Yeah, how would you comment on the recent trend that actually people are using different cryptographic solutions together, actually, like you mentioned, TE, FHE, MPC, and ZK?
I think this is the approach we have to take. That they all offer different benefits. You get different things from it, So I don't think it's a silver bullet. I don't think one technology will necessarily just win on this. As I said before, for instance, even if you're doing fully morphic encryption, you still need the CK proof of correct inputs in order to not leak anything. One issue we also have, and that's where MPC comes into the picture, is if you want to mix the data between the users and the different contracts, you need the data to be encrypted under the same public key. Otherwise, it's not compatible, and you just get noise out of it. So all the data on a given blockchain, we're encrypting that under the same public key. But that also raises the question of who has the corresponding decryption key, because whoever has that can decrypt all the data. So we have a KMS solution as well, a key management solution, where we're hanging on to the private decryption key and making sure that this can only be used in an authorized setting. So that's one of the extra things we're doing besides building TFHE-rs into blockchains. And that KMS solution, you can base it on multiple things. You could base it on a T, but in our case, we decided to base it on MPC. So this means that the secret key, the secret decryption key or the private decryption key, gets secret shared among a number of parties. And then whenever you want to do a decryption, you have to run an MPC protocol between these to do the actual decryption. And then no one gets to see the actual secret key. And we can also do so that no one gets to see the actual plain text that was decrypted. One benefit we get from this is that we now have a KMS that can be shared across multiple parties, so we can mitigate the risk of someone breaking one KMS. We can also decentralize it in a secure way and so on. So in that sense, we already have a CK and an MPC in our solution with fully morphic encryption.
It sounds like a paradise for cryptographers, I have to say. I want to ask about the KMS from the product angle. I can understand the cryptography, at least the basic level, but maybe you can explain more about like the features or what was the driver to come up with that in the context of like the blockchain product. Like, is this kind of like complementary to the coprocessor in some way? Like, what was the need, like decentralization and so on?
So it was really this thing that if there is in the normal blockchain use case, users will have their own private signature key, and they keep this that's their wallet, right? They keep this in the wallet, and then whenever they want to sign an operation, they can do this locally. And all the users, they have their own signature key. And we went back and forth on, do we want to have one encryption key per contract, one encryption key per user, and so on. But then we really lose this ability to mix data between different users and different contracts. So in order to get around this, we made the decision, and this is tweakable in the system. So if you want to have multiple keys on the one blockchain, you can do that. But in the general case, you typically want to have one key on the blockchain so that all the data is mixable, and you can run this auction, for instance. Using where the auction itself is then using a token as settlement and so on. And then that's really the question of, then is not a single user that owns the key, but rather some entity on the side. And then the question is, who is this entity? Is it, in the beginning we looked into using hardware security modules as well as a KMS solution, where we would simply buy an expensive card, right, that is somehow tamper evident at least, and then put the key on there. But we decided this was hard to decentralize. So in order to do this, we ended up with an MPC solution where we say we might still use Ts, we might still use HSMs together with this, but at least we can take the key and we don't have it in a single place, and we can distribute across, let's say 10 nodes. That each have to, a certain threshold of those have to agree that, okay, now decryption needs to take place. Yeah.
I want to jump into another topic. We already mentioned these in this conversation, but trying to take more of like the adversarial approach here, because there is a trend about for using these for confidential computing. And I'm curious about your take on how they compare with fully homomorphic encryption. I mean, one example, concrete example is, NVIDIA, the AI the machine learning line of products here that you mentioned. So NVIDIA, they introduced in the previous generation, they introduced this confidential compute that basically allows you to run on the same GPU that you run the machine learning workload, and have like very like almost zero cost in terms of the like the penalty on performance. And then you get confidentiality, you get verifiability, all the good stuff. So I'm really curious to hear your point of view as someone working on fully homomorphic encryption. How do you compare between the two, or like is there any kind of like real comparison? Even is it like really apples to apples, or you see it like as different things?
Yeah, and I think maybe another example is Apple and their confidential compute platform that they recently introduced, right, where they want to
Exactly.
offload some of the machine learning computations from phones onto their servers. I think that the very short answer is that we actually use TFHEs as well for a slightly different purpose, but we see a role in it as well. Our KMS solution is tied into or can take advantage of the AWS Nitro enclaves for some extra security. So again, I don't think it's a silver bullet. Having said that, TFHEs in many ways are easier to work with. We have a good library, TFHE-rs, that has a nice interface, is easy to use. We have the concrete compiler that allows you to write in Python and then compile this. So from a developer perspective, the superficial differences might not be that big. But in terms of getting the right performance, for instance, if you're doing a larger computation, TFHEs are definitely easier to work with because you don't have this overhead, as you also say. I think at the end of the day, it comes down to a trust assumption. There's been issues with secure enclaves in the past where people have hacked them, and then it turns out when it's based on hardware, it can be hard to update this. It can be hard to kind of recover to a secure state. In the blockchain space, there's also been various groups trying to use secure enclaves to build a confidential blockchain. So I do think it's something that's worth looking at. Technically, for sure, it's easier to work with the enclaves. You don't have the same kind of performance penalties. But with fully homomorphic encryption, you get a security that's based on the mathematical properties of the encryption scheme. Of course, the implementation needs to be correct as well. But security is not based on a given hardware module. It's not based on a company that manages to produce this hardware in the right way. And I think for some applications, TFHEs make a lot of sense. We think in the blockchain use case, fully homomorphic encryption has some nice benefits. It plays into or has some of the desired properties that people would like to have from decentralization, for instance. It becomes very easy to onboard new people with this. I think, yeah, at the end of the day, it comes down to what kind of, can you get people to trust in your solution? And I think here, TFHEs, historically at least, has a reputation for not being great. But again, we're also using them for certain things.
I think the probability of a bug in like NVIDIA confidential compute is likely 100%. But it also raised the question of what Zama are doing against bugs. Like, do you have some kind of an effort? I mean, besides being open source, to increase robustness?
So we do bounties to get people not only to work with the system, but also to discover issues. We do audits, both of the core libraries, but also the products that we're building on top of the core libraries. Of course, internally, we're publishing the core algorithms academically. As you said, everything is open source, so people can come in and have a look at it. And I think, yeah, that gives us some confidence in the implementation. But of course, yeah, bugs do happen, and it's been more on the performance side of things, that we can do something like a small bug would change performance. There is an ongoing discussion about what are the secure parameters to use for the given encryption scheme. This has been going on for ages with other schemes. RSA in the beginning were using small keys, and then you have to increase the key size and so on. The same applies to our encryption scheme. And over time, these parameters need to change. So there's a discussion about what are the right parameters to use, what is the good trade-off between performance and security. One of the reasons that we use the CK proofs for inputs is to prevent selective failure attacks, where someone can make what looks like a ciphertext, but is actually leaking something about the key if it's being decrypted and so on. And picking the right parameters for this is also an ongoing process. But one of the benefits we get there is to do this in the open academically, where we get people from the academic community to help weigh in on what are the good security properties to use.
For the blockchain use case, there is a concern about post-quantum security in many of the existing blockchains. Is this something that, if I'm using Zama fully homomorphic encryption, I'm going to have some kind of protection against?
So the scheme itself is post-quantum secure. And I think overall right now we're using some components that may not be post-quantum secure. For instance, in the KMS, we're using MTLS connections between the different peers when we run the protocol as a way of getting secure channels. And I'm not sure that's using a post-quantum scheme. But the underlying encryption scheme, TFHE-rs, or TFHE, is post-quantum secure. So it's more a question of, is the entire system around it then also post-quantum secure? But these are also the easy things to change. These are not directly related to our technology. So as soon as the industry is moving to using TLS that is post-quantum secure, then the system would also migrate to this.
Got it. Okay, so I also wanted to kind of like pick your brain on different like use cases that you might have seen. We've talked about open source, bounties. I know that Zama codebase is a favorite in hackathons. So are there other things, or even like specific to blockchain and AI, it's also fine, like some proof of concepts that you've seen in the wild or that have been using your code that you are excited about?
I mean, so one is the sorry. One is the token, the encrypted token, right, where people can keep the balance of an ERC20 token encrypted and only see themselves. That one's an easy one, but it could have a big impact. We have some discussions where instead of having a permission blockchain or a private blockchain, people could now potentially start using a public blockchain, but keep the balances encrypted, so obtain the same or achieve the same results, but using one of the existing big public blockchains instead. We've seen people get excited about the auctions, where you can tweak the auction mechanism since it's on encrypted data. We've seen people looking at distributed identity. So what you would typically prove, how the solution would work is that you would have your credentials or your attributes on chain, but in some kind of encrypted or committed form. And then when you want to prove that you are above a certain age or have the right for something, you would send in a zero knowledge proof with respect to those commitments to prove that, okay, now you actually you satisfy this property. What you can do with FHE instead is you can keep your encrypted data on chain, and then when you want to prove something, you would just do the computation. You would simply take your birth date and compute that you are above 18, and then decrypt only the Boolean result of this. So you can replace a lot of the CK solutions around distributed identity with FHE as well, where when you want to prove something, you simply compute and then do a decryption of this predicate for it. So this has been interesting as well. We didn't really touch on it before, but I think one of the good things around CK versus FHE for keeping stuff confidential on-chain is that the developer experience, I kind of hinted at it, I guess, but the developer experience doesn't change a lot. So you essentially get some encrypted data types to work with, but then otherwise everything else is the same as before. So this means you're not breaking up, you're not changing the way you write smart contracts compared to CK solutions, or at least some CK solutions, where it's really a paradigm change that you have to fit into this given framework for it. In the FHE case, you're just getting encrypted data types that you can compute on, and then you can decrypt sometimes. So the developer experience around building applications, in some cases, seems much more natural compared to how you would do this in plain text. But yeah, distributed identity could be one example of this that we've seen interested in. We've also seen some people using this for games. You can think of playing poker on-chain. You can think of it as playing, we had one doing kind of like a detective game on-chain was a fun application of this. But where you can keep the game state on-chain and encrypted and still compute on it, and then only reveal data as you go along. I think those are probably the biggest use cases we've seen for now. You can advance all of them, go in different direction, add more things to it. But I think that's a nice group of what we've seen so far.
Anything to do with AI agents, since it's really a hot topic recently in the crypto space?
Around AI?
Yes.
Yeah. I mean, so we do have, in the blockchain space, we've seen less of it. But as I mentioned before, we do have the concrete compiler, which can take a Python program and turn it into an encrypted computation. We also have concrete ML, where we have some optimized models, so taking scikit-learn models and then optimize them for the encrypted setting. So it is something we're looking into. The downside there is the computational overhead. It's quite significant. So you can do this today. We have a few Hugging Face demos actually, where I think one of them is around a sentiment analysis, where you would type in some text and we'll try to analyze the sentiment, but on encrypted data. But this will, I think we will see more results with this when we get better compute capabilities, so with custom hardware and so on.
Cool.
And I don't think we've seen much. The discussion comes up sometimes if we can do this on chain, and in principle you could, but again it's a question of compute cost, if this is really solving an actual problem or if it's worth paying for.
One thing I found that's quite interesting is that I remember Zama stating that it wouldn't launch any tokens. Is that still the same case? What is the ultimate goal for the project actually?
In the crypto space, so for now we don't have our own blockchain, right? We're providing the technology for other people to build their blockchain with this. We're providing with the co-processor to work on Ethereum. So we have moved into the service space a bit, where we're now offering services for run this stuff on Ethereum. But I think for the end game on the blockchain space, I think it remains to be seen. For now, we're happy to build these as services, and whether or not we would have our own layer 1, for instance, I think we see a lot of potential in being in the big ecosystems, for instance, being in Ethereum around this. And at the core, we are also a cryptographic company. The majority, so the blockchain division is around 20 people now, out of a total company size of around 70. So a lot of it is focused on the core cryptography part of it. What the future will bring concretely around blockchain and tokens and so on, I think that remains to be seen.
Mm-hmm. Got it. And what does your research pipeline look like?
So we do have a group of good researchers who are focusing on optimizing the scheme. But then we also get to influence the roadmap in the sense that we, for instance, for the CK proofs that we need for inputs, we could say, oh, we would like you to tweak them so that verification time is short, because this is what has to be done in the FHEVM native case. This is what has to be done by the full node. So it's very limited how long we actually have for verifying a given proof. But since it is the user working on the browser, it's okay if it takes a second or two to generate the proof. So in that particular case, for instance, we would go to the research team and say, okay, we have a slightly different requirement where we want verification time to be very short, but proving time can be a bit longer. And then they work on that. Sometimes another issue is we say, okay, we want storage of ciphertext to be relatively small, so we can put the ciphertext into the transactions themselves. So can you find a way of kind of compressing the ciphertexts that in other applications would not be a priority? So I would say that the research flow is, we do have a fundamental research goal of improving performance for the implementations, but also for the algorithms themselves. But then we also get to influence the research roadmap to say, okay, we have this in the given scenario for this to be efficient on blockchain, we would like this and this and this, and then they start looking into that. Another example is we can use the encryption scheme to generate randomness, in the sense that if you're in a smart contract and you want to play a game, you need to at some point to flip a coin. And what we can do is we can generate a ciphertext that encrypts a random value. But we can do this on-chain, so we can do this in a deterministic way. And that was also something that the research team came up with that was a bit, that was driven by our roadmap. And then they disappeared for a while and they came back saying, okay, here's a solution. What they then do is that they publish this, right? They go to academic conferences, and we try to be transparent on all the research that we're doing.
Mm-hmm. Got it. I guess now is the time to bring our last question. So, Morten, could you please name a project you're bullish about?
A project I'm bullish about. I mean, are you looking for outside Zama or inside Zama?
Both okay.
Both okay. I really like this co-processor approach that we have, because it solves a lot of the issues that we've seen before, namely this availability on different platforms, and also in a way subsidizing the compute overhead, where we can really scale out stuff, and then it offers many of these things as a service instead. So until we have, let's say, custom hardware, we can do horizontal scaling of the coprocessor for the computation, so the user still gets a good experience. And then as we get better and better performance, as we get new hardware, custom hardware, the user will get the same performance, but it will be cheaper for us to run. So this means it turns it around from being a question of latency and throughput to being a question of how much do you pay for it, or what is the cost that we have for this. And I think this approach of doing things like getting consensus on what needs to happen on chain, but then doing the heavy lifting off chain, I think that applies to other cases as well. This could be machine learning, for instance, where on chain you agree, okay, we need to run this prediction, but then running the heavy model is done off chain, for instance, using a coprocessor. I think some projects are looking at ML coprocessors, where this is a bit how it works. So this idea of putting heavy computations off chain, but still getting some on-chain commitments, I think that's interesting.
Right. I think that's it. Morten, thank you so much for joining us today. It was great catching up on Zama's progress. I hope we can talk again soon. For those interested, we are adding some links in the show notes. And that's it. Thank you, Queenie.
Thank you both. This was great. Good questions.